Hello, in this video I'll be working through Unit 2 homework problems 3 through 7. For number 3, we're asked to use the limit definition of the derivative to find the derivative function. Our function f of x equals 1 over x. So to find f prime of x, we take the limit as h approaches 0 of f of x plus h minus f of x over h. That's going to be the limit of 1 over x plus h minus 1 over x all over h. Now to simplify the complex fraction, I'm going to multiply top and bottom by x times x plus h. So I'll distribute in my numerator. When I multiply 1 over x plus h times x plus h, the x plus h's cancel out, and I'm just left with an x. And then the 1 over x times x plus h, the x's cancel out, so I have x plus h. All of that over, in the denominator, x times x plus h times the h that was already in the denominator. Simplifying my numerator, I have x minus h, so those cancel out, over h times x plus h, and then I'm just left with a negative h in my numerator, so the negative h divided by h just becomes negative 1 in my numerator. So now this is the limit as h approaches 0, negative 1 over x times x plus h. We can find this limit using substitution, so I'll substitute 0 in for h, and I get negative 1 over x times x, or negative 1 over x squared. So that is my equation for f prime of x. Part B, our function f of x equals x squared plus 4. We want to find f prime of x, so f prime of x equals the limit as h approaches 0, f of x plus h. So f of x plus h means we're going to substitute x plus h into the function. So we get x plus h squared plus 4. That's f of x plus h. Minus f of x. F of x is just our original function. All over h. Now we're going to simplify the numerator. In these problems, our goal is always to be able to cancel out the h in the bottom. So we're hoping that we can somehow simplify our numerator to the point where we'll be able to factor out an h and cancel it with the h on the bottom. So let's simplify the x plus h quantity squared. We'll expand that into x squared plus 2xh plus h squared. Then we have our plus 4. Now the minus x squared plus 4, we need to distribute that negative, so we have minus x squared minus 4. All of that is over h. Now I have some like terms that we can combine. X squared minus x squared is 0. 4 minus 4 is 0. So this becomes limit as h approaches 0. In my numerator, I have 2xh plus h squared. I'm going to factor an h out from that, leaving me with 2x plus h. And then we have our h in the denominator. So we cancel out the h from the top and the bottom. And we just have the limit as h approaches 0 of 2x plus h. We can find this limit using substitution. I let h equal 0, and I get just 2x. So my derivative equation, f prime of x, equals 2x. Part C, f of x equals x cubed plus x. We want to find f prime of x. So f prime of x equals the limit as h approaches 0. F of x plus h means we go to our function f and we substitute in x plus h. So we get x plus h cubed plus x plus h. That's my f of x plus h. So I need that minus f of x, so my original function, x cubed plus x, and all of that is over h. Now I'm going to simplify the numerator to the point where I can factor out an h. X plus h, that quantity cubed, so let's do that in 2 steps. That's going to be x plus h times x plus h times x plus h. Or to do this without having to write it all out, I'm going to think of it as x plus h times x plus h squared. And the x plus h squared, I can do that one in my head. That's going to be x squared plus 2xh plus h squared. I still need to multiply that out, but let me simplify the rest of what we have up there. So it's plus x plus h minus x cubed minus x all over h. Okay, so still working on simplifying my numerator. I am going to, let's just distribute the x first, and then I'll go back and distribute the h. So x times x squared, x times 2xh, x times h squared. Now I'm going to distribute the h, so I get plus hx squared plus 2xh squared plus h cubed, and then the rest of it plus h minus x cubed minus x. All of that is still over h. So we have x cubed minus x cubed, that's 0. I have x minus x, that's 0. And I think that's the only thing I can cancel at this point. Now in the numerator, every term that's left has an h in it, so I'm going to factor out an h from the numerator. Factor out an h, that leaves me with 2x squared plus xh plus x squared plus 2xh plus h squared plus 1 all over h, and then my h's cancel out. And now I can find this limit using substitution. So if I substitute 0 in for h, I'm going to have 2x squared plus 0 plus x squared plus 0 plus 0 plus 1. And I have like terms here that I can combine. I guess I could have done that earlier, but that's okay. So this is 3x squared plus 1. That is the equation of f prime of x. Number 4, we're asked to use the alternate definition of the derivative. So that alternate definition of the derivative is the limit as x approaches a of f of x minus f of a over x minus a. So we want the limit as x approaches a. Now I could go ahead and substitute 2 in for a right now, and that's fine. We can work through the problem that way. But I would prefer to just leave it in a for right now and wait until the very end, and then I can let a equal 2. And the only reason for that is maybe if I had multiple values of a, I could save myself the work, because if you put the a in right from the beginning, then each different value of a, you're going to have to work the whole problem out because it simplifies a little bit differently along the way. So I'd rather just leave the a in there in general, and that way, if I had multiple values of a, I could just substitute them in at the end. So the first thing I need in this formula is f of x, and f of x is just my original function, 1 over x. Minus, and now I need f of a. F of a just means go to the function f of x and substitute a in for x. So that's 1 over a. And all of that is over x minus a. Okay, now if I find this limit using substitution, I'm going to get 0 over 0, which tells us nothing about the limit. So we have to simplify this algebraically. This is a complex fraction, so I'm going to simplify. Here, let me erase this. I'm going to simplify by multiplying by the LCD on top and bottom. So the LCD is x times a. I'm just going to multiply top and bottom by xa. So like so. So we have the limit as x approaches a, and now I am, let's see, I'm distributing this to both terms in my numerator. So 1 over x times xa is just a, minus 1 over a times xa is x. And then in the denominator, I have x minus a times x times a. Well, a minus x and x minus a, those are just opposites. So if you divide a minus x by x minus a, you're left with just a negative 1. Or another way of thinking about that is I can factor out a negative 1, and then I would have negative a plus x, which is the same as x minus a. Okay, so I can cancel the a minus x with the x minus a as long as I leave behind a negative 1 there. So now I have limit as x approaches a of negative 1 over x times a. And I can find this limit using substitution. If x is approaching a, then we can substitute a in for the x. And this limit then just becomes negative 1 over a squared. Now we were asked to find f prime of a. This is f prime of a. But we were also asked to find it for a equals 2. So f prime of 2 would equal negative 1 over 2 squared, or negative 1/4. Part B, f of x equals the square root of x plus 1. We want to find f prime of a when a equals 3. And we're using the alternate definition of the derivative. So f prime of a equals f of x minus f of a over x minus a. F of x is the square root of x plus 1, okay, minus f of a is the square root of a plus 1 over x minus a. Oh, I forgot my limit. That's important. We limit as x approaches a. Okay, now to simplify this, I need to multiply top and bottom by the conjugates. Square root x plus 1 plus square root a plus 1 over the same thing, square root x plus 1 plus square root a plus 1. Okay, so that's the limit as x approaches a. So I'm multiplying these together. I need to FOIL this out, but when I'm multiplying by the conjugate, I really just need to do first times first and last times last, because the outer product and the inner product will cancel out. So square root of x plus 1 times square root of x plus 1 is x plus 1 minus, and then negative root a plus 1 times positive root a plus 1 is just a plus 1. And that's over x minus a times the square root of x plus 1 plus the square root of a plus 1. So limit as x approaches a. In the numerator, x plus 1 minus a minus 1. So this plus 1 minus this 1 is going to be 0, and I just have x minus a in my numerator. And that's going to cancel with the x minus a in the denominator, leaving me with just square root x plus 1 plus square root a plus 1 in the denominator, and leaving me with just a 1 in the numerator. So now I have limit as x approaches a of 1 over the square root of x plus 1 plus the square root of a plus 1. And I want to find f prime of 3. Oh, I'm not finished taking my limit yet. I'm getting ahead of myself. Okay, so now I find this limit using substitution. So I'm going to substitute the a in for the x, and I get 1 over the square root of a plus 1 plus the square root of a plus 1. And we can simplify that as 1 over 2 times the square root of a plus 1. So that's my f prime of a. If I want f prime of 3, now I substitute 3 in for a. So I have 1 over 2 square root 3 plus 1, or 1/4. Part C, find f prime of a for a equals -1. We're using, again, the alternate definition of the derivative. So f prime of a equals the limit as x approaches a, f of x minus f of a over x minus a. So this is limit as x approaches a. F of x is my original function, 3x squared, minus f of a, we're just replacing the x with an a, so 3a squared over x minus a. Now I'm going to factor out a 3 from my numerator. Leaving x squared minus a squared, and that's the difference of squares. I can factor that. Into x plus a times x minus a. And now I have a common factor that I can remove, the x minus a's. So that simplifies to the limit as x approaches a of 3 times the quantity x plus a. We can evaluate this limit using substitution. We substitute a in for the x, and we get 3 times a plus a, or 3 times 2a, or just 6 times a. That's f prime of a. If I want f prime of -1, I'm going to replace the a with a -1. So I'd have 6 times -1, or -6. Number 5, we're given some clues about a function f of x, and we're asked to sketch a possible graph of f, and then a possible graph of f prime. So we're told f of x is differentiable for all x in the set of real numbers. That means that the derivative exists at all x values. So when we draw our derivative graph, we're not going to have any holes in the graph, no asymptotes, no jumps. It's just going to be connected across our entire domain. And we're also given some information about specific points. We're told that f of -2 equals 1. So on the original function, the graph passes through the point -2, 1. So let's go ahead and plot that, -2, 1. So the graph of f passes through this point. I know that for sure. And I know the derivative at -2 is equal to -2. So the slope of this curve at this point is -2. If I were to draw a tangent line at that point, passing through that point, it would have a slope of -2. So I want to make sure when I draw my curve, it looks like it has a slope of -2 right at that point. So basically, like on either side of the point, it's going to be coming in like that. Now the rest of the information we're given all has to do with the derivative. We're told that f prime of -1 equals -1, but we're not told what f of -1 equals. So I'm not sure, when x is -1, I'm not sure how high up or how far down to draw that point. We're not told that. So we're just going to have to decide that for ourselves. Again, we're drawing a possible graph of f. There's no way to figure out like the one right graph of f of x with just the information that we're given. So I know that the slope is -1, and then when x is 0, the slope is 0. When x is 1, the slope is 1. And when x is 2, the slope is 2. So when I graph the derivative, those are points on the derivative graph. So let me go ahead and call this graph over here f, or f of x, and then this one over here is going to be the graph of f prime, or f prime of x. So I can plot the points on the derivative graph that I'm given. F prime of -2 equals -2. So I have a point here. F prime of -1 equals -1. F prime of 0 equals 0. F prime of 1 equals 1. And f prime of 2 equals 2. So it's pretty clear from what I've drawn so far that the derivative graph is linear. And I know if my derivative graph is a polynomial in degree 1, that my original function is going to be a polynomial in degree 2. So now I have a better idea of what my function f is going to look like. I know that the graph of f is going to be a parabola. So let's go back and try and sketch out f. Again, I don't know for sure exactly where the points are going to pass through, but I know what the slope of the curve is going to be at -2, -1, 0, 1, and 2. If I know that f prime of 0 equals 0, then when x is 0, the tangent line is horizontal, so that's where I'm going to have the vertex on my parabola. So I'm just going to kind of make this, I'm just kind of guess that my parabola is going to look something like that. I'm trying to make it symmetric here, doing my best. And let's see if this will work. So at x equals 0, we do have a slope of 0. If we imagine drawing our tangent line, it would be horizontal there. So at -1, we should have a slope of -1. And yeah, I probably could have done a little bit better with that. This is difficult to draw with the pen. Okay, coming in like that. At 1, the slope is supposed to be 1. So at this point here, yeah, that looks pretty much like a slope of 1. So I'm happy with that one. And then at 2, I should have a slope of 2. So right here, yeah, that pretty much looks like a slope of 2. So that's about what our function for f is going to look like. Now for part C, we are asked to make a conjecture. So that's just means kind of make a guess about the equation for f and the equation for f prime. Well, I can find the equation for f prime more easily just looking at the graph that we drew and the pattern that every time x increases by 1, the derivative is increasing by 1. So I'm pretty sure my f prime equation is just f prime of x equals x, right? If we look at our values, f prime of 0 is 0, f prime of 1 is 1, f prime of 2 is 2. So f prime of x is x. The equation for f of x is a little bit harder to guess. But looking at what I drew, I mean, it pretty much looks like I drew the graph of y equals x squared shifted down 2. So I'm just going to go with y equals x squared minus 2. And then we were also asked, okay, so if we think the graph of f, or the equation for f, is x squared minus 2, to use the limit definition of the derivative, define the derivative and show that it's equal to the equation that we came up with for the derivative. So f prime of x, I know, is equal to the limit as h approaches 0 of f of x plus h. So I'm going to use my function f of x and I'm going to substitute in x plus h. So I have x plus h squared minus 2. There's my f of x plus h minus f of x, and that's just my original function. So x squared minus 2 all over h. So we're going to simplify that. In the numerator, I have x squared plus 2xh plus h squared minus 2 minus x squared plus 2 all over h. So our x squared minus x squared is 0. That cancels out. Minus 2 plus 2, that's 0. That cancels out. Now my remaining terms have an h, which I can factor out. And if I factor an h out of the numerator, it's going to cancel with that h in the denominator, leaving me with 2x plus h. And here, if I find the limit using substitution, if I substitute 0 in for my h, then I just get 2x. So this is not exactly the equation that I had for my derivative, which means that either the equation of my derivative is wrong or the equation of f is wrong. And since I'm pretty confident that the equation of my derivative is right, I mean, we have pretty strong evidence based on the points we were able to plot that our derivative is right. Okay, that tells me that the equation I came up with for f of x is probably not right. And since I've already learned how to take antiderivatives, I actually do know what the correct equation is. The correct equation for f is 1/2 x squared. And I could still shift it down 2 if I wanted to, so we could go with this. That would be a correct equation for f of x, but it's okay if you don't know how I came up with that. We really haven't learned that yet. We will eventually. Number 6, part A, use the limit definition of the derivative to determine a formula for g prime of x. So g prime of x equals limit as h approaches 0, g of x plus h. So we're going to substitute in x plus h. That's g of x plus h, minus g of x, that's our original function, all of that over h. Okay, so we need to simplify the numerator. X plus h, that quantity squared, is x squared plus 2xh plus h squared. Now I distribute the negative, so minus x minus h plus 3, and distribute the negative again, negative x squared plus x minus 3 over h. And we have an x squared minus x squared. We have a 3 minus 3. We have negative x plus x. So now this is the limit as h approaches 0. 2xh plus h squared minus h over h. And we can factor in h from the numerator, leaving us with 2x plus h minus 1 over h. H's cancel. If you're using this limit definition of the derivative and your h's don't cancel, you know you did something wrong along the way algebraically. So that's kind of the whole goal here, is to get that h to cancel out that's on the bottom. So now we have limit as h approaches 0, 2x plus h minus 1. I'm going to find this limit by substituting 0 in for h, and I just get 2x minus 1. That's my equation for g prime of x. Okay, then we are asked to sketch the graph of g and g prime. You can use your calculator to graph this. I don't have mine handy, so I'm just going to plot some points. When x is 0, g is 3. So a point here. We'll call that 3. And when x is 1, g is also equal to 3. And I know that this is a parabola that opens up, and by symmetry of the graph, then the vertex has to be halfway between those 2 points. So at 1/2, I have my vertex. So let's see, 1/2 squared minus 1/2 plus 3. So 1/2 squared is 1/4. 1/4 minus 1/2 is negative 1/4. So the vertex is going to be a little bit lower than 3. We'll just put it like here, I guess. And then our parabola opens up. Okay, now if we want to sketch our derivative graph, we have the equation for that. That's down here, 2x minus 1, y equals 2x minus 1. So that is a line that has a y-intercept at -1 and a slope of 2. So we have a point at 0, -1. We have a point at 1, 1. We have a point at 2, 4. I guess. Now we're not drawing a tangent line, so it's not a concern that these graphs don't look like they're intersecting. That's fine. So this one is G, not F. This one is G prime, and this one was G. So our graph of G is decreasing until we get to an x value of 1/2. Okay, so this is the point where the graph of G stops decreasing and starts increasing, or if we picture tangent lines, it's where the tangent lines change from having a negative slope to a positive slope. So it does make sense that on our derivative graph, right at 1/2, is where our graph changes from being negative to positive. So a negative graph means below the x-axis, positive graph means above the x-axis. So these two do seem to go together. Part C, use the limit definition of the derivative to find a formula for h prime of x. H prime of x will be the limit as h approaches 0. H of x plus h, so using h as the name of the function probably isn't a good idea in this case. Don't want to confuse my h's, but I'm going to stick with it. So we have 5 times x plus h squared minus 4 times x plus h plus 12. That's my function evaluated at x plus h, minus the original function, 5x squared minus 4x plus 12, and all of that over h. Okay, so we need to simplify our numerator. X plus h squared is being multiplied by 5. So I have 5x squared. My 2xh gets multiplied by 5, so I have 10xh. Then my h squared gets multiplied by 5, so 5h squared. Okay, now I distribute the negative 4, so I have negative 4x minus 4h plus 12 minus 5x plus 4x, or minus 5x squared plus 4x minus 12. All of that over h. So we have 5x squared minus 5x squared is 0, minus 4x plus 4x is 0, plus 12 minus 12 is 0, and the 3 remaining terms in our numerator all have an h in them, so I will factor out an h, leaving me with 10x plus 5h minus 4 over h. Then my h's cancel out. And using substitution, this limit is equal to 10x minus 4. Now, if we think about the results we've seen on this problem, when our equation was x squared minus x plus 3, our derivative was 2x minus 1. And when our equation was 5x squared minus 4x plus 12, our derivative was 10x minus 4. And then we are being asked in part D, how do the constants 5, 4, 12, and 3 affect the results? Well, let's start with the 12. Like, here's 12, and I don't see 12 anywhere in my derivative, so that doesn't seem to have an effect. And the same is true over here with the 3. Here's a 3. I don't see a 3 anywhere in my derivative. That doesn't seem to have an effect. Now the 5 and the 4, okay, the 5 I don't see right away in my derivative. However, if I multiply 5 and 2, I get 10, and I do see that in my derivative. So let's see if that the same is true over here. If I multiply the 1, the like hidden 1 that we see in front of here, if I multiply those two numbers together, I get 2, and I do see that in my derivative. And then it's asking also about the 4. Well, I have a minus 4 in h of x, and I also have a minus 4 in my derivative. Does that same pattern seem to apply for that previous problem? Well, I have a negative 1 in front of my x, and then I have a negative 1 in my derivative. So it seems like there might be a pattern here. And in fact, let me write a new equation. I'll just make something up. So if we have f of x equals, let's go with 3x squared plus 7x plus, we'll say 5. Can you guess, just based on the pattern that I've shown you in the previous two, what the derivative is going to equal? Well, if we have the same pattern continuing, then multiplying those two numbers should give me the number in front of x in my derivative. And then this number should probably come down, and this number is not going to have any effect at all. And in fact, my derivative, f prime of x, is going to be 6x plus 7, so that pattern does hold. Now, before you get too excited about that, this pattern that I'm showing you only works when your function is quadratic. So if we have our quadratic function in standard form, then it's going to be true that we can get the derivative quickly kind of by recognizing that pattern. But we are going to talk more about shortcuts when it comes to finding the derivative. We're not quite ready for that yet, but soon, I promise. Okay, number 7, we are given the graph of f, and we are asked to sketch the graph of its derivative. And we're told that we should be using a scale of 1 in the horizontal direction, that we may need to change the scale in the vertical direction, but we'll just see if we need to do that. So the first graph on the left is made up of a bunch of linear sections or linear pieces. So this one is going to be fairly easy to find the derivative, because on a linear function, the derivative is just the slope, and the slope is constant. So we should be able to find that pretty easily. So in this very first piece, just using rise over run, I can see the slope is -2. And the slope is -2 all the way up until like this x coordinate right here. So we're going to assume that's an x value of -3. So on my derivative graph at -3, or until -3, so I should say from -6 until -3, the slope is -2. So my derivative graph is down here. Now, right here at this point, the slope is undefined. So we talked about this in class, but if you zoom in really close on that graph, no matter how close you zoom in onto that corner, it's still going to look like a corner. It's never going to appear linear. You're always going to have that corner point there. So the derivative is not defined there. The slope of the graph is not defined at that point. So I'm going to have an open circle at -3. Now we have another linear piece in our function f between -3 and -1, and the slope there is just 0. So when I sketch my derivative graph, my derivative should be passing through 0 for all x values between -3 and -1. And again, at this corner, the derivative doesn't exist. So I'm going to have open circle here to here, and the derivative is at 0 in between those 2 points. The next piece has a slope of 1, and that's between -1 and +1. We have a slope of 1, derivative not existing at those corner points. Then from 1 to 2, the slope is 0. So I'm back on the x-axis here. And from 2 to 3, the slope is 2. From 2 to 3, the slope is 2. So I'm up here. And then from 3 to 5, the slope is -2. And finally, from 5 to 6, the slope is 0. So we'll say derivative doesn't exist at the endpoints there. Our next graph. Okay, so I'm going to start with this point right here, trying to find the derivative at that point. Well, the tangent line, if I draw it, will be horizontal at that point. It has a slope of 0. So the curve has a slope of 0 at that point. So my derivative graph is going to pass through 0, 0. And then I'm going to try and just visualize where the slope is equal to 1. So maybe right around here. It looks like if I were to draw a tangent line, I think the slope would be equal to 1 right at that point. So I'm going to follow that down and say the slope is going to be 1 at that point. Okay, and then on the other side, sort of same distance away, the slope at that point is going to be -1. So follow that one down, and I have a point at -1. Now, where's the slope the steepest? Okay, if I'm kind of imagining drawing a bunch of tangent lines along my curve here, I think it is going to be steepest where I've already placed those points. Okay. And then the graph, the slope is approaching, like on the right-hand side, if I start drawing like tangent lines, they're getting less and less and less steep. They're approaching 0 as I go to the right. So when I draw my graph, my derivative graph here, it should be getting closer and closer to 0. Not actually reaching 0, just getting closer and closer to 0. Like so. And then the same on the other side. The slope is just getting closer and closer to 0. It's not actually going to reach 0. And then I'm just going to sort of connect these in between like so. Okay, our next graph. Now, we've got some pieces that look kind of linear or like they have a constant slope. So I'm going to graph that first. That seems to be like easiest. So this section of the graph here, from between 3 and 6, that's linear. It has a slope of 1/2, up 1 over 2. So between 3 and 6 on my derivative graph, the slope is 1/2. So I'm just going to draw it at 1/2. Slope is 1/2, and since there's a corner point at 3, I have an open circle there. The derivative doesn't exist at a corner point. Now we also, it looks like the graph is pretty linear between, let's say, -3 and 0. It looks like it has a slope of 2. So between -3 and 0, we have a constant slope of 2. At 0, there's a corner point there, so open circle on my derivative graph. Now between 0 and 3, that looks like a quadratic function. It's a degree 2 polynomial, so my derivative is going to be linear. At 2, the tangent line would be horizontal, so at 2, my derivative is going to be 0. At 1, the derivative looks like it's a little bit steeper than -1. So maybe a little bit further down than -1, maybe like right there about. And when I'm really close to 3, not right at 3, but really close to 3, if I draw like a tangent line and try and picture like rise over run, it looks like my slope is about 2. I'm just going to go with 2. Looks like it's maybe about 2. So I'm getting kind of close to here. Okay, so now if I think that my derivative is linear in there and I've got these 3 points, I can kind of sketch what that derivative is going to look like, and it doesn't exist at 0. So I've got an open circle there, open circle on this end, like so. Okay, so now we just have to figure out what is going on between -6 and -3. Well, between -6 and -3, it looks like I have another like parabola again. So at -2, the slope of the curve is 0. So right here, I said -2, I meant -4. At -4, the slope is 0. And let's see if we can pick out where the slope is going to be 1. So a slope of 1, it has this kind of angle to it. If I'm imagining drawing a tangent, maybe like right about there, the tangent line looks like maybe it has a slope of 1. That might be a little bit steeper than 1, so we move it down just a little bit like here. And then slope of -1, that would be coming in at like this angle about right there. So if I kind of move that onto the graph or try and picture where that's going to occur, I'm thinking maybe about right there. The tangent line would have a slope of -1. So following that down, -1. Okay, and I've got my points. Now the derivative does exist here. Okay, so I'm going to go ahead and just connect this up. I don't have an open circle there. And follow my derivative down like that. Now our last graph, let's see, our function, it's increasing and then decreasing, increasing, decreasing, increasing, decreasing. And there are several places here where I can see the slope is going to equal 0. So I will plot those points first at our maximums and our minimums. So we have a 0 here. If I follow this one down, right here, 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 here. Our original graph is very symmetric here, so I'm expecting my derivative to also look pretty symmetric. Now, if I try and find where my derivative is equal to 1, again, a slope of 1, it's coming in at, that's not quite right. I want like a 45-degree angle. So I'm trying to imagine where the tangent line is going to look like that. So if I kind of bring that down to the graph, maybe, you know, like right here. If I drew the, no, that's going to be more like that. So that's not quite it. I have to get even like closer to the top there. Let's just kind of estimate, let me just estimate what the slope is at this point right here. So if I draw a tangent line, or imagine zooming in really close on the graph there, what's the slope going to be? Well, probably around 3, I would say. At that point, the slope is 3. So also right here, I mean, the graph is symmetric, so that I'm going to also then put the slope being 3 right there. And also this point right here, follow down, I'll say the slope is 3 right there. And then on the decreasing side, kind of along those same lines, I'm guessing the slope right there is -3. So that puts me there, there, and there. And again, it's okay if you didn't get these graphs, to be entirely accurate, but we're working on using some of the clues from the function of f to plot some key points on the graph of the derivative.